I'll start my presentation with the introduction, but not mine, but the protagonist of our speak. And this is this guy, and this is like the question to the community. Does anyone know what his name is? No, someone? Come again? No? It's not. Exactly, yes. Later on I'll buy you a beer at the party. So yeah, so this guy is Red. He's like protagonist of our talk here right now, but he is coming from this game. If you haven't played it, I highly recommend it. It's super cool. It's everything started. So he basically, like all 10-year-old in the Pokemon world, wants to be a Pokemon trainer. So he approached this guy, which in our story will be product owner, to get his Pokemon and start the journey. But the product owner, it's like, you know what? I have a business idea. We'll do different way this time. Every 10-year-old wants to be a Pokemon trainer, so we'll create the app. We'll add some games then we'll multiply those games by 17 and the kids will add their parents' credit card and we'll be rich, basically. So we'll create the app that will be gathering all the information about Pokemon, so whoever is using this app will be basically better with the fights or whatever. And we'll call this app. So this is how the app will look like. So we'll have all the information about the Pokemons, and we will call the app Pokedex, right? And this is part 1. This is about data normalization, and this is my name. So yeah, let's start. So our protagonist had some information in mind. He saw the design for like split second, but who cares? So he decided that he'll just gather information about the Pokemons, and they'll have some name, some information about statistics, because there was something type, who's he strong against, who's he weak against, and what type of attack he has. And he filled it with the first Pokemon. Yeah, nothing fancy. So then the first fight has happened, and he had information about the another one, and another one, and so on. And then something happened. New business requirements has arrived, right? So our professor told us, you know what? The Pokemon can evolve. So basically, when they fight long enough, they can change their form, whatever. Just add it to the table because this is very important for our end users. So he's like, okay, no problem. Just add another column, call it like next form, fill it out. We're done. Ticket closed. We're done. Yeah, for the day. Great success. And here, continue his journey. There is another Pokemon, but this one apparently doesn't have next form, but who cares? Let's keep filling. And then another business requirement has arrived. Yeah, we know the story. So now it turns out the Pokemon can have multiple moves. So they can attack this way or another way. And yeah, he was like looking at his table and said, okay, this is no-brainer. Let's just change the name of this column to moves. And just add here, whatever. We're done. Again, ticket closed, great success. Yeah, we're done. But he's starting to noticing some problems. And he was like, okay, I'm not very good at my job. I just started and I'm 10 years old. But I can see that there is starting to be a mess in the statistics. And since I know that there is staggering amount of 155 Pokemons, the professor for sure will hire more guys who will be writing to the table, and there will be even more mess. And I can see that I started with writing like attack, defense, but then I make it at def and then again. So if it grows, it will be messed up. So, we need to fix this somehow right now when it's relatively easy to do. So let's write down this problem in our backlog, that not atomic values can lead to inconsistencies. It's like some more professional. And let's split it because it's quite easy. So we'll be just keeping number. It's super easy now. It's hard to make a mistake. We don't have any fields right now in the, at least here, that are like ambiguous. Okay. But we fixed one thing, but moves are not, right? We have like non-atomic values here. So yeah, we are not really done with the problem, but we will see. Maybe it will solve itself. And we can see that editing is also not easy. This is the problem number 2. Because let's say that it turns out that this grass type of Charmander or whatever he's strong against needs to be changed to black for some reason. But does it mean that this grass also has to be changed to black or not? And the weak versus it's also, you know, this thing is like tricky. So let's write another thing to our backlog, which is like some values has to be edited in multiple places, right? And let's go back to our journey. So yeah, we found another Pokemon, filled out our database, and we start noticing some pattern that we have empty spaces. Is it good or is it bad? We don't know, but since we're like in the time where we had staggering amount of 4 megabytes of memory, it may be problematic, but just to be safe, let's add it to our backlog. Empty cells. We don't really want them because they're just keeping place, right, in our table. Okay, we can see, or not we can see, but our protagonist realized that this rock thing is actually not the Pokemon. It was just a rock, you know, but who could know it? And he wants to get rid of it, right? Because we don't need this information. But if we remove it, we'll lose information that the rock type is strong against fire and weak against grass. So we kind of can't do it, right? We have some useless information which is really tightly linked to some information that we want to keep in the DB. So let's write another problem. Maybe it will fix later, hopefully. That deletion can lead to unwanted data loss, right? We want to delete one thing, as we can see, but we are losing information that that is valuable to us and we won't keep there. And in our case, it's like we can't store data about the types, just exactly what I just said, right? So yeah, we'll end up with almost empty row. And you guessed it, new business requirement arrived. And this time, our professor is like, you know what? Those Pokemons, they are supposed to have the IDs. And yeah, I mean basically this. So they should be identified not only by the name, but by the ID. And hopefully, it was quite easy to implement because we're just adding one column at the very front, add some IDs, and that's it. We're done. Finally, no problems. We have finished some ticket. And we have improvement idea that we can use those IDs, for example, to address the Pokemons in the next form. Because what if we have this Charmeleon, if we make a typo, it will lead nowhere. So let's change it to ID, and let's change it to numbers. So then it's much harder to mess up, right? To make a typo when we are typing 4 than Charmeleon. Easy, right? Okay, and yeah, just like in usual life, new business requirements have arrived. And it turns out the moves also have types. So apparently the Ember move is type of fire, and it means something to our end users. And the move of Bubble has also the water type, for example, and we need to keep this in database. But it's kind of hard to do. But fortunately, we are involved in Pokemon, and our table has just evolved. So from this, it has changed to this. And we no longer have the problem, right? Because now what happened, if we have separate row for like Pokemon move combination, right? No longer non-atomic values. We are good. We can easily add a column, name it move type, fill it out with all the data that is needed, and you guessed it, we are done, ticket closed. Yeah. We are safe. Okay. So our table has just evolved to stage 1. So yeah, let's take a look at our problems, and we can tell that we no longer are suffering from the first thing, right? We don't have non-atomic values anymore in our table. Great, we have done nothing and some problems have disappeared. This is what we'd like. But it wasn't free, we have a lot of duplicated data, right? Because, like I said, every Pokemon has now, it's not like a table about the Pokemon, it's a table about the Pokemon linked with the move. Like, because Charmander has like 2 records, Squirtle 2, and the Butterfree guy has like 3 records per one Pokemon. Okay, but fortunately enough, our table is evolving again, because, yeah, plot armor. So from this, we have started, our table has just started changing, and we can see that we can like kind of move type around. So let's take a look at this. We can remove duplicates, because in this table, we don't really need to know twice that Ember is fire type and Ember is fire type, because come on. Here's another duplicate, so let's get rid of them. Let's add them IDs, because we know that IDs are really good. And let's name this table, because right now we have 2 tables, Pokemon and moves. So let's name it moves. So this has just been moved outside. So we are left with something like this. And we can see that here we ended up with a lot of duplicates, which can safely delete, because they're not adding any value to our table. So yeah, let's get rid of it. Let's clean it up, remove all the gray stuff. And our Pokemon's table looks like this. But we need one more thing that will be linking our Pokemon's table with our moves table. So it will be basically like this. So it has Pokemon table on the left, the move on the right. We have changed, instead of move name, we are using move ID. So it will be something like this. And it will have a name. According to race convention, it should be move Pokemons, something like this, because it's there, but I name it Pokemon moves anyway. And we can delete, it was supposed to delete the empty row, because it's not having any information. And from this, we have evolved to this. So we have table that is holding information about Pokemon, about the moves, and like table in between them that is saying which Pokemon has which move. Great. Let's go to our problems and see which of them has just been resolved. So we don't have empty cells, almost. And we don't have any duplicated data. That's great. Okay. And yes, you guessed it, now the table is evolving again to get rid of magically of all our issues. If we take a look at Pokemon's table, there is some data that is not really depending on the Pokemon, but it's depending on the type, right? The fact if the Pokemon is strong against some type doesn't depend on the Pokemon itself, but the type itself. So we'll do very similar thing here. We'll like take those data, extract it, name the table, add the IDs. So instead of names, we have IDs, because strong versus another type, and so on and so on. And remove this from the main table. So here we are also using IDs. And that's it. Our Pokemon's table has changed to something like this. So we have Pokemon's moves, types, and Pokemon moves, which is like for some reason missing here. So yeah, let's go back to our problems. The values don't really have to be edited in multiple places. We can store now the information about types only, and rows deletions is safe. But it all comes at a cost. And now if we're looking at our data structure, and let's say we want to read something about, this is about removing unwanted data, which we can do apparently right now without losing anything else. So yeah, let's get rid of this, and let's remove the last of our problems. And now let's get back to our table. And let's say that we want to learn something more about the Butterfree. So we can see that in the main table we only have information that its type ID is 4, so we need to go to another table, find the type with ID 4. Okay, this is the bug type, we know which is strong against and which is then. And then let's go to the Pokemon moves. Okay, this is the ID of the Pokemon is 5. So we can see that those are the move IDs that we want to read, and so on and so on. So the downside of this data structure is that the reading is complex. So yeah, let's go to the summary. But no worries, this is summary of the part 1. So if instead for problems we would be saying those are anomalies, and instead of evolution tiers we will be calling them normal forms, it will actually mean that we have done the lecture on database normalization. And the thing to remember is the higher the form, the lower the redundancy, so less redundant data we have. The higher the form, the higher the data integrity, so it's easier to break something. So because you have to, I don't know, rename Pokemon just in one place, not all across the table. And the higher the form, the longer the read time is. So it's like the cost of it. So that's pretty much it for the part 1. And we're jumping to episode 2, because why not? And episode 2 starts with cold open with our favorite business requirement. So yeah, we have a data structure ready. So our business owner comes to us and say, you know what? That's great, it's working, but we actually need some data there because it's otherwise useless to our users. Okay, so let's do it. And I was doing this animation so long, so you have to watch it full. So yeah, we were starting to adding more Pokemon and more and more. And this is time to sip of water. Yes. And we are filling them, you know, boring stuff. Okay, so let's end up with 32 Pokemons. Yes, I know this is like huge data set, but it's enough to see some records, and this is how our table looks right now. And we received another business requirement. That business owner comes to us and say, you know what, our core functionality, which is finding Pokemon by name, is not working anymore. It's slow. You have added so many records that now we are waiting in seconds to retrieve them. Fix it. Okay, so it's time to debug. Let's say that we want to find the Charmeleon. Okay, so let's go. Oh, here it is. Okay, it wasn't that bad. It wasn't that long. What the hell does he want, right? But since we are all engineers, we know that, you know, maybe we got lucky this time. So let's find another Pokemon. This time, this one, for some reason. Picked randomly, and turns out it's at the very end of the table, and actually it takes quite a lot to go there, right? Look how many comparisons do we have to do, because we're just basically going line by line, line by line. Okay, here it is. Okay, so the good news is we identified the root cause, but we remember something from, you know, reading articles, going to studies, and so on, that when data is sorted, it's easy to find, right? So let's do it. Our table is evolving. We have this time some magic control over it. So what we are gonna do, we're gonna change our table so it's sorted by the name this time, right? Yeah, it must work. Let's find Charmeleon again. So once, because this is sorted, we can go to the middle and say, okay, this is metapod, M is like after C, so we can just drop everything what's below. And let's go again to the middle. Okay, this one is harder because it's CHA, but yeah, we are dropping everything above, and go again to the middle, and again. Okay, we found it. So we are great, we are happy because we solved the issue, we sorted the table, and the finding should be much faster, right? But unfortunately, we learned that we broke something, because now finding Pokemon by ID is not working at all. Yeah, so this is the episode 2. It was like really long cold opening, but episode 2 is called Indexes Start Back, and yeah, it's again my name. So okay, so what we can do? We can do the easiest thing to like undo the unwanted changes, which is git revert and push to production, right? Because we can see that names are in order, but IDs are not in order. So yeah, let's undo our changes. magically. And we need to get deeper. We need to understand what the heck has just happened, what's going on there. Okay, so this is our table. And it turns out it's not really a table. It's not really a table. It's an index, which is not in form of like regular table, but B3. Does anyone remember what B3 stands for? No, not binary. Binary tree was basically what we're doing with just jumping in half. So this is balanced tree. It's slightly more optimized than binary tree because it's easier to write and read. And this is a very interesting data structure that has leaves, branches, and a root. And it works more or less like this, that when we want to find a Pokemon with ID 7, we are starting with the root, finding a number 8 which is greater than 7, then going to the branch, and yeah, it helps us to find something in the data structure really relatively fast. Most of those structures, like in live production, doesn't have more than, I think, 4 branches, something like this. And the sizes of the leaves and everything has been chosen totally randomly right now, just to show some idea. But yeah, it is the data structure that helps us finding in a large data set which has 32 records really fast. And this is what actually we have in place. Probably different development team has done it in the so-called meantime. So there is more interesting thing about this particular thing, because it turns out that this is like index organized table, and this is organized by indexes, and it has very, like, again, I would say in the same sentence for the third time, word interesting. Those blue numbers are representing like addresses on the disk space, whatever. They're totally arbitrary, doesn't mean sense. And in theory, those things can be scattered all over the disk. I mean, you get the idea. And let's say that we are doing, I don't know, some pagination, something like this, and want to display those 4 Pokemons. It turns out it will be scattered all around the disk space, and we will have to do a lot of reads. I mean, 4 reads or 3 to retrieve them. So the index organized table has a very interesting attribute, which is the data is like organized. So when it's next to each other in the table, it's actually next to each other in the disk space. So now, when we want to read, again, just those 4 things, for example, we're doing pagination and just want to display those 4 records, they're next to each other, and it is highly probable that we'll get them with just 1 read. So yeah, so we dig into it, understood why another team has done it, because they're just working with the finding by index for some reason. So we can go back to the business. Okay, so turns out that, I mean, we don't want to touch the table, right? Because it's already organized by the indexes. So we will create another index just for the names, which will be saying, okay, so this Pokemon has this ID. So yeah, it's basically like this, and it will be sorted, because we all saw that finding in a sorted array is much easier. So they will be basically sorted by name, and they will be pointing to the ID of the Pokemon, which is like the main base is started. So we'll add this additional data structure. It will be obviously the index, which will look like this, and we should be good, right? Yeah, so this is our index, and it is called secondary index because we have like main index on main table, and this is like additional data structure. But then again, never-ending story. The business guy comes to us and see that it's slow. It's too slow. It has to be faster. We are losing customers. We are losing money. The parents can't stand crying kids. Will disconnect their credit card and will be lost. Okay, so it's another debug time. This time we need to figure out what's going on, and let's see how the search is looking. So let's say that we want to find the Charmeleon again for some reason. And we need to search through this index, like we saw earlier. And from this index, we'll learn that his ID is number 4. But then we need to find this index again. And it turns out that we are doing 2 searches, right? We are first doing first search for first index, and then we are finding the record, the Pokemon, which is like organized by the ID. Okay, so we need to fix this somehow, and we have brilliant ideas. Instead of saying, okay, this is the ID of the Pokemon, we'll be saying, okay, this is the place on the disk where the Pokemon is, right? So we can do something like this, and we'll be keeping in the index its physical address, and we'll be simply saying, oh, where's the Charmeleon? And we'll say, oh, over here, right? Without traversing through the second index. And it will be much faster, and our product owner will be finally happy with us, and finally we can close this ticket. 1 search needed only. Excellent. The new business requirement alive. You don't believe it, right? Turns out that they found some new Pokemon which needed to be added to the table. So let's do it. This one will be easy. I mean, at least should be. So yeah, let's go to the bottom, to the very bottom of the table. Let's add new one. We're done, at least in this part. But we remember that also indexes has a names. But indexes is not a table that we can just add. We need to add some, moving data around. It doesn't really matter what's happening now, but yeah, we need to change this. But this indicates change over here and over there. But it's doable. It's doable. We can handle it. We have done it. And so yeah, so changing the names index was a bit more tricky than just adding to the table, but we have managed. In turn, we got another business requirement that we are supposed to remove Pokemon from the table because they got extinct or whatever. We don't want to keep them in the table and occupy our precious space. So turns out that these guys, because they have rat in the name and they were eradicated, whatever, let's just remove them. But here is where the problem is happening, because we know that the idea of this table was to keep the things next to each other, right, on the disk space. So we were ending up with this, with A21 and A22, the place where everything down has to be moved up, right? So we need to do the rewrite. So yeah, we can kind of do it, but it's a lot of work. And we have to do the same thing in the name index. We have to do a lot of rework just after removing two Pokemons. Our table is evolving. And let's see what happened. Probably because it turns out that deleting is like messing our data structure, and we need to make it otherwise. So instead of using like this index organized table, we'll simply use secondary index also for the IDs with the names. So as you can see, we have our table in which we don't care anymore about ordering them, placing them together, and so on, which leads to tricky editing, removing, and inserting. And IDs table, which will be basically saying, okay, the Pokemon with ID this lives here, and Pokemon with IDs this lives there. So yeah, so the table when we don't really care about the order or like the placement of the data is called heap table, and it is not being moved. And now if we are readdress our issue and try deletion again, it will be like this. We are just removing them and we're done. We don't care because yeah, the addresses of everything below is not changing at all. And here it will be like this, that we want to get rid of those 2 records, we're removing them, and we're done. Okay, so let's try insertion to the table, because it turns out that our research data was wrong, and those Pokemons are not extinct anymore, for some reason, right? Who could know? So instead of rebuilding all the table, because this is like a heap, we can just add them here, because we don't care anymore about the order, and we are done. And same thing here. We just adding the records in the right place, because we know that it has to be sorted. They're pointing into the address on the disk drive, and we're also done. So the summary, finally. Index up, speed up the search. We saw it. They are allowing to find things faster. But there are additional data structures, so it comes at a cost. They have to be built, rebuilt after some operations. And by default, table is a heap. This is what we saw at the very end. No one is really using the index organized table. And this is time for the questions, because I think I'm done. But please bear in mind that my GitHub account has been created, this is really small, like in 2016. And before that, I was doing animation for the Pokemon. So yeah, thank you so much.
Thank you. Thank you, Mateusz.